Y'all happy to be here today? It's like a Friday, huh? Like a Friday, sort of? Yeah. You out here, the speakers in the back? Oh, the mic. All right, is that better? All right, cool. Any big plans for the weekend? The fall break coming up? Going home? You're from up north, right? Like Oklahoma. Work. Homework. Homework, yeah. I think it's a lot of exams next week after the break. Oh, today maybe. Yeah. We're just gonna hang out. We're going camping actually on Friday and Saturday nights. We'll be gone all weekend. We're going up to Palmetto Island State Park. Ever been there? No, it's a pretty new park. It's only like 5 or 6 years old, but it's a nice park. Lots of good canoeing. Gonna, I don't know, do camping stuff, build a fire, hang out. We will have our exam next week, and it will cover the part of Chapter 3 that we missed last time, the projectile motion, and all of Chapter 4. We're going to wrap up Chapter 4 today, and then we'll have some time. So, Tyler, what I told you earlier is incorrect. Okay, I'm sorry about that. But it will cover all of Chapter 4. And we still have two main things, and they're kind of big things, the inclined plane and friction. Friction's not that big of a deal, but the inclined plane is, and it's sort of an extension of what we've been doing. So let's jump right in on that, and we'll let you have some practice with the inclined plane. You know, all along here, we've been following a process where we label all of our forces, we resolve our forces into our x and y components. We've only done that once or maybe twice, but we resolve them into our x and y components. And then we apply Newton's second law. And remember, Newton's second law was that the sum of the forces equals mass times acceleration. But in particular, we can be more particular, rather, in that we can say the sum of the forces in the x direction is max, and the sum of the forces in the y direction is may. And so we're going to do that today, looking at an inclined plane. So this is an inclined plane. You'll have a couple problems on your test that deal with an inclined plane, 2 to 3 problems that deal with it. And you need to be able to tell what are all the forces that are at work on an inclined plane. And if you have an inclined plane, these are definitely 2 of the forces that you would have. So let's do a couple problems. We'll do this next problem, which is from your MCAT, from the MCAT prep book. But let's first just look at this problem and say that we have, I don't know, a 10 kilogram block. Let's say that the mass of this block is 10 kilograms, and let's say that this angle is 30 degrees. And I want to know now what acceleration is it going to have? What is the acceleration going to be as it goes down the inclined plane? Now the acceleration is not going to be 9 or 10 meters per second squared like it was in free fall. It'll be less than that because it's going down an inclined plane. I've already labeled all the forces that are at work here. We have our force weight. By the way, we know what our force weight is. If it's 10 kilograms, the weight is going to be 100 newtons. So hopefully that's sort of second nature to you now. I just say 10 kilograms, force weight, equals m times g. That's 10 kilograms times our acceleration due to gravity, which is 10 meters per second squared, which gives us 100. We don't know what the normal force is right off, but we can find it, and we will find it later. I've also drawn the x and y coordinates here. Now, there are a couple ways that you could draw the x and y coordinates. Don't draw this, but this is one way that you could do it. You could draw your x and y coordinates like that. But that's not the way that we're going to do it, so I'm going to erase that. Instead, we're going to draw our x and y coordinates so that they fall along the plane of the incline. So we're going to let our x-axis fall along the plane of the incline. Our positive x will be in this direction, and our negative x will be in this direction. So that's a little counterintuitive because going up the inclined plane is the negative x direction. But it will be important because we're going to, the signs will tell us which direction our object is going. It's not terribly important, but it's sort of important. Now, I can redraw this. I'll draw my coordinate systems over here, and then I can just redraw my vectors. I have my normal force vector, Remember, the normal force is perpendicular to the surface. So I've drawn it here, perpendicular to the surface, so that this angle is 90 degrees. Notice that this coordinate system has been rotated, and so when I rotate it back over here, it's sort of our normal plane, my normal force is along the y-axis. And then I can also draw the weight right here. This is my normal force, and that's my weight. Now, one of the tricky parts about this is figuring out the angle. So if this angle is 30 degrees, what is this angle right here? This angle is 60 degrees. You can see there is a triangle right here. I have a triangle right here. If this angle is 30 degrees, that means this angle is 60 degrees, and that's the same angle as this. This angle, by the way, would be 30 degrees. There are sort of different ways to approach this. I'm always going to measure my angle from my x-axis, so I'm not going to use that 30 degrees. Instead, I'll use the 60 degrees. My next step is going to be resolving the vectors. So I'm going to redraw this, and I'm going to resolve my vectors. I'll have my normal force here. That is along the y-axis, so I don't need to do anything for that. And then I'm going to have the x component of Fw. What is the x component of Fw? It's going to be Fw times what? Cosine of 60. Right. So that's going to be Fw cosine 60. And then similarly right here, I'll have Fw sine of 60. Now let me just make this point. I'm not going to do this in class, but sometimes you might encounter this. Like if you're pre-med, you'll probably see this in your MCAT prep. If you're doing the online quiz, actually there is a question where this comes up. But I can also write these as Fw sine of 30 or Fw cosine of 30. These statements are equivalent because the sine of 30 is equal to the cosine of 60, and the sine of 60 is equal to the cosine of 30. So there are two different tacks that you can take on this, whether you use the angle 30 degrees or the angle 60 degrees. But because we've already been dealing with the x component always being the cosine, I'm going to use our angle as it's measured from the x-axis. But just be aware that this comes up sometimes. It does come up on your quiz at one point. I think where you have to give, I forget exactly how it comes up, but it does come up in the quiz at one point. I think you have to give the equation for the x or y component of something. Am I right about that? It does come up? Somebody, maybe not. Okay. That quiz is due tonight, by the way. The reading assignment and the other assignment. Okay, so now that I have my forces resolved onto x and y components, I can apply Newton's second law. I can say that the sum of the forces in the y direction equals MAY, and the sum of the forces in the x direction equals MAX. The forces in the y add up to give me the mass times the acceleration in the y, and the forces in the x give me the mass times the acceleration in the x. What is my acceleration in the y direction on this inclined plane? This block, presumably, is moving up or down this inclined plane. We know it's actually moving down. But what is the acceleration in the y direction for this case? It's not negative 10. I know what you're thinking, that all along as we've been doing free fall, that in the y direction it's been negative 10. But notice how we've rotated our coordinate system so that the y-axis is along this direction. So when I ask you what is the acceleration in the y, what I'm asking is, what is the acceleration as it moves along this y-axis? And is it moving along that y-axis? No, it's not. So the acceleration then is 0. That's always going to be the case for our inclined planes. It will always be the case that the sum of the forces in the y is equal to 0 because the acceleration in the y is equal to 0. Now, the acceleration in the x direction is not 0. And so in this problem, where if I wanted to know the acceleration, this is what I would consider. The sum of the forces in the x direction is equal to max. Okay, so I'm going to come over here and look at the forces in the x direction. I only have one force in the x direction, and that's that Fw cosine of 60. And that is going to equal to my mass times my acceleration in the x direction. I'm looking for the acceleration, and so I want to calculate this. I'm going to say that ax is equal to Fw cosine of 60 divided by my mass, right? Fw is m times g cosine of 60 divided by m, and so that mass cancels, and it gives me my acceleration, which is going to be 10 meters per second squared, that's g, times the cosine of 60, so that'll be 8.7 meters per second squared. Yeah, 8.7. Okay? So that's how I would find the acceleration along this inclined plane. Now let's imagine a very similar situation, and that's what this problem right here is talking about. Let's imagine that instead of having it go down the inclined plane, I have this 30-degree inclined plane of this object, and I have a force that is holding it up. And I want to know what is the force that's holding it up. Yeah, time. Oh, is it 5? Okay, I'm sorry. Yeah. Thank you. Should be 5. Let's go back and just sort of take a look at our steps again. And then we'll approach this other problem. So the first step is we draw our coordinate system. With the inclined plane, it's always going to be the same. I have my y-axis perpendicular to the incline, and my x-axis along the incline. Then I ask myself, what are the forces? The simplest, like this, is I just have two forces, and those two forces will always be present. I have the normal force, and I have the weight. The next step is I want to think about the angle. If this angle is 30 degrees, that means this is 90 minus 30, or 60 degrees. And so this is 60 degrees. And then I want to redraw this. You know, you might even do this on the exam. I always do this whenever I work an inclined plane problem. I rotate my coordinate system, because I can do that. I choose the coordinate system, but I can rotate it however I like. And I redraw my vectors. My normal force is along the y-axis, as I have it over here. And then my weight is at 60 degrees below the x-axis. The next step, I draw my coordinate system, label the vectors. I redraw this. This is called a free body diagram, by the way, a free body diagram, where I just draw the vectors and I don't have the object listed there. I have my weight, my normal force. The next step is to resolve the vectors into their components. I have Fn, and then I have Fw sine 60, Fw cosine 60. That's the x and the y component of the weight. Now that I've gotten that, I apply Newton's second law. And now it's really just an algebra problem. I have the sum of the forces in the y direction is 0. That's always going to be the case for inclined plane problems, because your object is never going to move off of the inclined plane. The acceleration in the y direction will always be 0. Sometimes the acceleration in the x direction will be 0 if the object's not moving at all. But if it is moving up or down the inclined plane, then this acceleration will be non-zero. Next, I recognize that I want to know ax, because that's my acceleration. And so I take the equation that I create from Newton's second law, and I solve it. And in this case, it's fairly easy to solve. There's only one unknown. I say Fw cosine 60 equals max, and I solve for the acceleration. Okay, that's a good example of the type of problem that you'll have on the exam coming up on Wednesday. There can be some slight complications, and we'll get into those today, but not terribly more complicated than that. But if you haven't seen it before, I remember the first time I saw the inclined plane, it's like, what? you talking about? So you'll need to spend some time practicing. There's some homework problems. Look at all the old exams. They all have inclined plane problems on them. You will definitely see inclined planes next Wednesday. You're probably going to see up to 3 questions with an inclined plane. Like I'll have one question that's, calculate this or that, maybe another question where you calculate something, and then a question that asks more of a conceptual thing about it. I'll show you some examples of those. Now let's ask this question. What if I wanted a force so that the block is stationary? What if I wanted a force so that the block is stationary? Well, I can go back and imagine putting in a force right here. I want a force acting on that object so that it is stationary. And now when I write my Newton's second law, it's going to be a little bit different. I'm going to write the sum of the forces in the x direction. Will you take just a moment and write out the net force in the x direction as we've listed it here? What is the vector sum of these 2 vectors? And then we want to solve for what that force should be. Which is going to come first? Now in the x direction, I only have FW cosine 60 and I have F. So it's going to be some vector sum of these. Which one's going to be positive? F or this FW cosine 60? The first or the second one? The second one's going to be positive because look, it's positive x right here. This is negative x. Remember, if you're looking at the inclined plane though, it gets a little hinky because it looks like this is positive because it's, pointed up the inclined plane. So don't fall for that trap. This one is going to be positive. F is going to be negative. So I'll have FW cosine 60 minus F. And now we want to think, what is it going to equal to? I'm going to go ahead and write MAX. But if I'm looking at something that's stationary, then AX is going to be, what do you think? 0. It's called a statics problem where AX is equal to 0. Now I can solve this for F. F is equal then to FW cosine of 60. And that's going to be 100 newtons. Because remember, this was 10 kilograms. 10 times 10 is 100 times cosine of 60. So that's going to be 50 newtons. That force has to be 50 newtons. While we're here, let's just camp out a little bit, because let's say that I wanted to know my normal force. And in fact, when we get into friction, there will be some cases where you'll need to know your normal force. So if I wanted to know my normal force, how would I do that? How would I figure out my normal force? If I go back to my vector diagram, and my normal force in the y direction, are there any forces in the negative y direction? I do. I have a component of the weight in the negative direction. If I didn't have a force in the negative direction, what would that thing do? It would fly up off the inclined plane because I don't have anything holding it down. So in order to have a normal force, I have to have some opposing force. Because remember, the normal force originates, or it arises as a result of, or rather, Newton's third law describes the normal force and what happens. So if I wanted to know the normal force, I would look at this. I would look at these forces in the y direction, and I'll just write it right here. I'll do the sum of the forces in the y direction is Fn minus Fw sine of 60. That's going to equal to 0. In the y direction, the acceleration will always equal 0 on the inclined plane. And then I can solve for my normal force. It's going to be Fw sine of 60, which is going to equal to 87 newtons. FW is 100 times sine of 60, which is 0.87, gives me 87. Okay, when we move on, we'll do some more practice on these, but I'll let you try some on your own. Okay? Smile. Smile. It's good? You look like you're not very happy. Or is it just me? Maybe, I don't really want to be here today. Y'all feel the same? We should all just go. Yes, but we're not going to, because you pay good money to be here, and they pay me good money to be here. Let's try this. Let me zoom this out a little bit. All right, let's try this. This is a block on an inclined plane. The block is accelerating up the inclined plane, it says. And I want to know which of the following equations will follow from the application of Newton's second law. I'm going to make one small change here right quick. I'm going to change this sine of 30 to cosine of 60. Because of that discussion that we had, sine of 30 is equal to cosine 60 in fact. And you can express it in either way. So just to limit confusion, I'll change that to cosine 60. So which of these equations will be correct for our application of Newton's second law? Now what you want to do, you'll draw your coordinate system. You'll figure out this angle. You'll resolve your vectors. You only need to resolve this one vector. And then you can go through and figure out which of these equations is correct or incorrect. If you don't have your workbook, I know you can't see those equations very well. Try to look on with somebody else on the other side. Most people have it. Which of these equations is correct? 3 are incorrect, 1 is correct. All right, y'all doing pretty good on this. We still have about 20 people that have the wrong answer. So feel free to ask your neighbor what they put. And then change your answer if you like. I'm going to stop in about 10 seconds. I'm going to stop at 250. 250. Okay, good. C is right. That's pretty decent for a first try. All right, so let's think about, first we're going to resolve our vectors. I'm going to redraw this. Let me blow out, just zoom out just a little bit. I'm going to draw my free body diagram. You might not need to do this. That's okay. This is my Fn. This is my F. Now I can resolve my F force weight into its two components. Up here I'm going to have Fw cosine of, what's my angle? 60 degrees. And down here I have Fw sine of 60. All right, because remember, this angle is 60 degrees. If this angle is 30, then the angle from the x-axis is 90 minus 30. Now I can also recognize that it's accelerating up the inclined plane. That means that I have a positive AX acceleration, right? Because this is the positive X direction, so my acceleration is in the positive X direction. Oh, it says it's accelerating up the inclined plane. All right. So now I can think of what my equations are. Let me just list the equations. There are only two, and then we can go through and show why each one is correct or incorrect. So the sum of the forces in the y direction is going to be Fn minus Fw sine 60. That's always equal to 0, because that block's never going to fly off of the plane. The sum of the forces in the x direction, which in this case is not going to be equal to 0, is F minus Fw cosine 60. And that's going to be equal to mass times acceleration in the x direction. All right, so let's look at these. A, Fn minus F. First of all, that's not on our list. But also, look, the normal force is here. This force is here. In these second law problems, these force problems, the x and the y variables, they're never going to mix. They're always independent of one another. This variable will be independent of this variable. So they shouldn't appear in the same equation like this one. So that one doesn't work. Here I have Fn minus Fw cosine 60 equals max. That's wrong for a couple of reasons. First of all, notice the normal force. Is that x or y direction? It's in the positive y direction, but it has an ax over here. So that's not correct. And besides, ay is equal to 0. And then also this Fw cosine 60, well gosh, it's on the x-axis. So these two vectors, they're not related either. C, I think, was the right answer. Fw sine 60 equals Fn. That's right here. That's this equation, but it's just solved for the normal force. And then also the third equation, Fw equals Fn. That's not true. Fn is equal to only a component of the weight. Usually, if we're on a horizontal surface, this is true, but on an inclined plane, it's never true. Okay? Yeah, William? For C?
Getting how it's the N, it's on the X. Because only way I can tell you is really I'm not. It's just not getting it.
Okay. Right here, you mean. This Fw sine 60?
That makes sense. It's just confused because of the previous problem that we did, and this one has the same instance where you take, like, why wouldn't it be 30 degrees to find the y and 60 degrees to find the x?
Oh, okay. I think I understand what you're saying. So once we figure out that this angle is 60 degrees, we forget about the 30. Okay? And then when we're finding the x component, it's always cosine of this angle. When we're finding the y component of the vector, it's always the sine of this angle. But you remember with our x and y components of our vectors, and just forget that this 30 even exists. And really what we're looking at is, let me redraw it over here. My Fw is right here, and it's at an angle of 60 degrees. So my Fwx, if this doesn't answer your question, let me know. But my Fwx, or excuse me, y, is over here, and it's equal to Fw sine of 60. And my Fwx is up here, and it's equal to Fw cosine of 60. These are my components of my vectors. So it wouldn't really make sense to say, I could say this was Fw cosine of 30, and I could say this would be Fw cosine of 60, but I think that confuses people, so that's why we're not using two separate angles.
So sine of 60 is the same thing as cosine of 30.
It is the same, right?
Okay, that's because the 30-degree angle that would mean sine of 30 or cosine of 30.
I did show you that in the previous problem, but just as a caution for you to be aware that you might see that in other problems at other places. But again, I'll write it again for fear of confusing you. And I know some of you are already confused, but this is equivalent to cosine 30. So cosine 30 and sine 60, those are the same. Okay, I'm sorry. Is that clear now? Okay, good question. Let's do some more practice, okay? I know that for some of you it's not clicking yet, and that's okay, but let's do some more practice. I think we're going to skip this problem because you're not going to see anything like this on the exam, and let's spend some more time on the inclined plane. The inclined plane is really, in my opinion, more important. So let's, I don't know if we have other, well, first we need to do friction, and then we'll come back to some inclined plane problems. Okay? Friction, we can have two types of friction. Actually, we'll have two sort of large categories of friction, and then we'll have two different types of friction in practice. We can think of them in two different scenarios. In macroscopic friction, like, you know, big scale, and microscopic friction. Macroscopic, you can think of these two surfaces coming together. And the crags on the surfaces just physically bump up against one another. And that friction causes your motion to slow down. It resists the motion. Sometimes we call these resistive forces, and that's why. You have a resistive force in your quiz with the rocket, with the 4 thrusters. Don't forget there are 4 thrusters on that, and you're looking for the thrust of one of those engines. So make sure you remember that when you work that problem if you haven't yet. Anyway, resistive forces resist the motion. In macroscopic friction, as I said, it's just a physical impediment. Or you physically obstruct the motion or stop the motion or resist it. They do this study, or they did this study, where you plot the friction versus the smoothness. And as you might expect, if they make these surfaces smoother, what's going to happen to the frictional force? It goes down. As you expect, you smooth them and they go down. And so they did this study where they found that this decreases, that as you make it smoother and smoother, it gets smaller and smaller. But something funny happens is that as you keep making it smoother and smoother, eventually you get a little uptick in the frictional force. Now, over here, this is going to be macroscopic, but this is explained in microscopic terms. Imagine that you now have these two surfaces. They're very smooth. What is happening to cause our frictional force to increase? Now, you can probably think of some reasons in your mind, but try just thinking of, there's a couple of reasons why it increases, so I'll tell you in just a second. But why would, as I make these smoother and smoother and smoother, why would the frictional force increase? Well, there are two reasons. The first reason is that as you make them smoother and smoother, you get more and more surface area that touches. Right? So more of the surfaces are touching one another as they get smoother and smoother. But that doesn't fully explain it. Really what's happening is something that's on a microscopic level, where you have charges in these surfaces, and they sort of bond together. They attract to one another, which causes that frictional force to increase. So that's kind of a curious thing. We'll come back to that later in next semester and talk about how that works. Yeah, this would be representing the microscopic friction. But on a microscopic level, the charges are actually attracted to one another. Okay, so two types of friction, but first of all, let me just point out that friction is always opposite the direction of motion. We'll see some very special cases, one special case in the concept test where it's not, but as far as we're concerned, it will always be opposite the motion. It's a resistive force, so it opposes or it resists the direction of motion. There are two types of friction that we're going to talk about. Static friction. Static friction we'll call Fs. And static friction acts on objects that are not moving. That are static or stationary. They're not moving. Don't go away. I'm going to come back to this. I just want to see something. Yeah. So static frictions act on objects that are not moving. We can calculate our static friction. It is less than or equal to mu s times the normal force. Now mu, this is the Greek letter mu, lowercase mu. It looks like an M, but I would try not to use an M. It's really a U, and it has a little tail. It's the Greek letter mu, but it looks like a U, and it has a little tail. I wouldn't write an M because then you'll get confused with masses. You just got too many masses around. But this is the Greek letter mu, and mu is the coefficient of static friction. It is a constant dependent upon the material. In fact, think about, it's actually dependent upon two types of material. So if you have, say, I don't know, rubber and asphalt, there's a certain coefficient of static friction between those two surfaces. On the other hand, if you have metal and ice, those are two different surfaces, and they have a different coefficient of friction. Which would be bigger, the rubber on asphalt or the metal on ice? Rubber on asphalt has a much bigger coefficient of friction. That's why we use rubber tires on asphalt roads, because our frictional forces are bigger, allowing us to, grip the road better. So this coefficient of static friction is just dependent on the material. And then you know the normal force, Fn, this is just our normal force. All right, so look. Can you help me? So, try to pull this. Okay, so you can pull it across the desk, even though there is a frictional force between the paper and the desk. Now, I'm going to push down harder. Can you try to move it? So if you can't move it, I've increased the frictional force. What have I done to increase the frictional force? Have I changed the makeup of the material? No. I've increased the normal force. So I increase the normal force, and that causes the frictional force to increase. So by increasing the normal force, I increase the frictional force. The frictional force is dependent on the coefficient and on the normal force. Now, there's this little pesky thing about this inequality here. This inequality occurs because imagine that you have a block or some heavy piece of furniture, and you push on it with a force equal to 20 newtons. And it doesn't move. The acceleration is equal to 0, so you know that the static frictional force must be equal to what value? If I have no acceleration, my net force must be 0, so the frictional force is 20 newtons. It has to be equal and opposite. So I'm pushing on this thing. I'm going to push on this with 20 newtons. That's about, what, 5 pounds of pressure. I'm going to push on it. Is it moving? No. So the frictional force must be 20 newtons in that direction. So that means that if I push with a bigger force, if my frictional force is 20 newtons, then I should be able to move it, right? I'm going to push with 30 newtons, and let's see what happens. You ready? It's not moving. Why is it not moving? What has happened to the static frictional force? It increases. And in fact, it will continue to increase. Even if I push here with 30 newtons, I get 30 newtons. If I push with 40 newtons, I get 40 newtons. It will continue to increase until it reaches this maximum value. So let's say that the maximum value is 50 newtons. This thing's not going to move until I get up to 50 newtons. And then I overcome the static friction and I move to something else. Declaring static friction, we're going to work some problems with it. But important things is dependent on the coefficient and the normal force, and that it has this inequality. So it doesn't have a particular value, it has a maximum value, but the static friction can be less than that maximum value. Now kinetic friction, which we call Fk, a lowercase script fk, acts on objects that are moving. And our Fk here is going to be very similar. It's equal to mu k times the normal force, where mu is our coefficient, but now of kinetic friction, and n is our normal force. Now, as I push on this thing 10, 20, 30, 40 newtons, it still doesn't move, but then I exceed the maximum static frictional force, then it starts moving, and that's going to cause kinetic friction to become in play. You've probably witnessed this. You ever moved a big piece of heavy furniture, like scooted it across the floor? If I have something, big heavy furniture, and I push on it in this direction, initially, it is hard to push. But after you move it, it is easier to push. It's easier to move. After in motion. You might have just thought that was in your mind, right? That I push a big heavy box across the floor. Oh, now I got it moving. Now it's easy to move. But the fact is that our coefficient of kinetic friction and our static friction are different. And when it's not moving, you're dealing with static friction. When it is moving, you're dealing with a different type of friction, which is called kinetic friction. For almost all materials, the coefficient of kinetic friction is less than the coefficient of static friction. You can try this today. You should try it as you leave. So as you're headed out on Maywood or wherever you're parked, let's go try something. You don't head out on Maywood, up the street, or wherever. Head out. So try something that you probably don't do very often. You're driving, you're listening to your TV or whoever, and you come up to the stop sign, and you know what you're going to do today? I want you to stop at the stop sign. And you'll witness this difference between static and kinetic friction. So come to a stop, and actually come to a slow stop. Right? Not a rolling stop, that's not really a stop, but a slow stop where you slowly push on your brakes and you slowly come to a stop. What happens at the moment that you stop? Sort of jerks a little bit, right? You know your brakes, you know how your brakes work? You have a rotor, it's like this disc of metal inside your wheel. There are two pads that clamp down onto that rotor. When the rotor's turning, what kind of friction is that? That's kinetic friction. And then, as the wheels slow down, at the moment they stop, the amount of friction goes from kinetic to static. And because there's a difference in the force, the kinetic and static friction, then that's why you get that sort of jerking motion. Try that as if you have a friend, tell them what's about to happen. If they're about to witness a mystery of nature. And they'll be, why are you stopping? Zoom right onto the stop sign. Listen, out in Mississippi where we live, there's a stop sign. And we never stopped at it. I never realized we didn't stop at it until my wife came out there with us. And she's like, do you realize that you just flew through that stop sign? I'm like, it's just like it's like a yield sign. It's not even a stop sign. All right, so try that when you go out. So you're going to see, I don't know that we'll work them today, but we'll see some problems in your homework and on Monday when we return. Problems on inclined planes dealing with friction. And that's going to complicate our inclined planes a little bit, but not too much. It's just going to you'll have to figure out what your normal force is, which you already know how to do, but it will complicate it a little bit. So let's do this problem where I want to know what is the maximum force so that this block will remain stationary. So I have this block, it has a mass of 1 kilogram. There's my coefficient of static friction. I'm going to draw these vectors on an XY coordinate system. There's my normal force. There's my weight. I'm going to go ahead and give you my weight. It's 10 newtons. And you know what? You can probably, without going through all the business of the sum of the forces in the Y, sum of the forces in the X, you can probably tell me right off what is the normal force. What is it? Well, duh, it's 10 newtons, right? So I say Fn equals 10 newtons. If you don't get that, let me show you. So I do sum of the forces in the Y is Fn minus Fw. That's equal to 0. So Fn must equal Fw. But as you practice with these and as you get more and more familiar with them, you'll be able to skip some of these steps. As you get more familiar, you'll be able to say, well, if this is 10 newtons, this has to be 10 newtons, because it's not moving in the Y direction. And then my force F is over here, and my force Fs is over here. I want to know what is F. I know from the sum of the forces in the X, which are equal to 0, as it states in the problem, it's static, that F minus Fs is equal to max, but a is equal to 0. So Fs is equal to, or excuse me, F is equal to Fs. Oh, but you say, that doesn't really help me that much because I don't know what Fs is, the static frictional force. But look, I can know it because I know mu s, and now I know my normal force. So I can say then that Fs is equal to mu times my normal force. That's going to be equal to 0.1, no units on mu, times the normal force, which is 10 newtons, and that's equal to 1 newton. So my maximum static frictional force is 1 newton. That means that F, which is really what the problem is asking for, is also 1 newton. Okay? Couple steps you had to take here. You had to find the normal force. I heard you had to recognize, I want to know F. In order to know F, I have to know the static frictional force. That is the maximum static frictional force. Once you exceed this force, the thing's moving. So if I want to know F, I have to find this. In order to find this, I have to find my normal force. The normal force is equal to the weight of 10 newtons. And so my static frictional force is mu times the normal force, or 1 newton. And then you say, well, that's my answer. It is 1 newton, wherever I wrote that. F is 1 newton. Okay? Another example of a type of problem that you could have on the test on Wednesday. Let's try this problem. Okay, doing really well so far, those of you that have answered. We'll do about 15 more seconds. Stop at 2:35. 2:35. All right, good. A is right. There's just a bunch of extra information in this problem. You have the mass, you'll need that to find the normal force. The normal force, if this is on a horizontal surface like it is equal to the weight. So the normal force, in this case, equals the weight, which is 100 kilograms times 10 meters per second squared, which is 1,000 newtons. Then we want to figure out which of these is the kinetic frictional force and which is the static frictional force. This one, the bigger of the two, is Fs. This one, after it's moving, is Fk. And we want to know what is mu, so we say Fk equals mu k times the normal force. And so mu is equal to Fk over Fn. That's 300 over 1,000, which is 0.3. So A is the right answer there. A. Okay, let's think about this. I'll let you go. I know you're itching to go. But let me also say something. I don't know that we're going to finish all the concept test questions, but I'm going to go ahead and post them online so that you can practice them over the weekend. So that you'll have them. We'll do some of them. Just a second, guys. Maggie? Yeah. Sure. I'll get to your question in a second. But I'll go ahead and post them, even though we haven't done all of them. I'll post them online. Maggie? Hey guys, what's going on? It's over. Simon? Right, Fk is 300 because it says after the crate in motion, the horizontal force is required to keep it. It's also the smaller of the two forces. Alrighty? It's a little early, but I'll let you know. It's okay. Y'all have a good day, okay? Have a good break. I'll send you an email sort of with what you already know about the exam, or what I've already said.